Okay, we're going to take another look at particle motion. We've talked about particle motion before, and this is a good time to review and just look at it one more time. Okay, so I'll leave that for you to read, except they do say something important about when we talk about particle motion. It does include horizontal and vertical motion of a falling object. So it's important to note that the motion meant the particle was moving along an axis, not along the graph of the function. Now it is possible for us to work in two directions. For example, if an object is traveling in a straight line, then its velocity can be expressed as the integral of acceleration. Okay, think about that, right? If we have acceleration, then we can use it through integration to come up with velocity. So now we will focus on gaining a better understanding of how to model the motion problems that will appear on the AP Calculus exam. Okay, so here's another idea that we should be familiar with, and that is of net change. It says the definite integral of the rate of change of a quantity f prime of x gives the total change or net change in that quantity on the interval. Okay, and we should be familiar with this idea. Let's say we have some derivative. When we integrate it, we get the antiderivative, right? The thing that we would have had before differentiation. And then we plug in the limits of integration. And basically what we get is the difference between those two things, right? So when we're integrating with definite limits from A to B, then what we're finding is the total change of the function, the antiderivative, between the points A and B, okay? So when we're talking about motion and velocity, there are three things that we might be asked to find. One is the displacement, okay? And when we talk about displacement, you know, that means you may have gone back and forth several times, but the only thing that really matters is the difference between where you started and where you ended, okay? So that's displacement, just the difference between where you started, where you ended. You might have been all over back and forth many times, but just what change was ultimately made. Okay, versus when we talk about total distance traveled, this means we're counting each and every step, right? Whether it was to the left, to the right, however many times you did it, we want to know the total distance traveled, okay? And so to do that, it's just going to be the integral from A to B of the absolute value of v of t dt. Okay, it doesn't matter about the sign. It's just going to be that. In this image, okay, normally, well, let's go back. If we were talking about displacement, I would subtract a sub 2, because it's below the x-axis. But if we're talking about total distance traveled, then we're going to make even those things that are below the x-axis positive. All right, so for displacement, it would be A1 minus A2 plus A3. But for total distance traveled, it would be A1 plus the absolute value of A2 plus A3. All right. And then the last thing is actual position. Okay. So start to think, and please make sure you pay attention to the notation here for the integrals. For displacement, just the integral from A to B of v of t dt. All right, that is, when you see that, you can think displacement when we're dealing with velocity and particle motion problems. And so when I look at that down here, again, this is displacement. So if I have an initial condition that identifies my position at the beginning of the process, then I'm going to add however much displacement there is, and that's going to give me my new condition. So these are the three things that they might ask us about: displacement, total distance traveled, and actual position. All right, so let's see if we can answer those things for this example. It says given S of 0 equals 4, find displacement, total distance traveled, and position on 0 to 10. Okay, where V of t is in meters per second. All right, so if I want to find my displacement, okay, we're looking at the integral from 0 to 10 of V of t dt. Okay, and basically I can just say 18 minus 12, right? We could have broken it up from 0 to 5 and then 5 to 10, but we get 18 minus 12, or 6 meters. Okay, we're integrating velocity, and remember the integral of velocity is going to be position, so we've had a displacement in our position of 6 meters. Okay, for the total distance traveled, that's going to be the integral from 0 to 10 of the absolute value of V of t dt. All right, so in this case, we get 18 plus 12, or 30 meters. Okay. And finally, to talk about our new position, okay, if we know that at time 0 we were at 4, because they told us S of 0 is equal to 4. Right. Then the only thing I really need to do is add my displacement. So we get new position is going to be 4 plus our displacement of 6. Okay, remember the formula looked like C, which was our initial condition, plus displacement. So in our case, from 0 to 10 of V of t dt. Okay, so our initial position is 4. We found that displacement is 6. So our new position is going to be at 10 meters. Okay, let's look at another example. It says the graph at the right represents the velocity of a particle that is moving along the x-axis on the interval from 0 to 8. And V of t is measured in inches per second. For what interval of time is the particle moving to the right? Okay, so remember the difference between velocity and speed is that velocity has a direction, right? And when velocity is positive, we are moving to the right. So when I look at this picture, I see that my velocity is positive from 0 to 3, right? You can see we got positive velocity. It's all above the x-axis. And then again from 7 to 8, all right? So for what interval of time would we have our particle moving to the right? Okay, because V of t is greater than 0, or maybe I should say when V of t is greater than 0, the particle moves to the right. Okay, this occurs for 0 less than t less than 3 and 7 less than t less than 8. All right, so that's when we have our object moving to the right. Okay. The next question is, on what interval is the particle slowing down? Justify your answer, okay? So we see a graph here of velocity, okay, but we might have questions about, well, in order to talk about whether or not it's speeding up or slowing down, we need to know about acceleration, okay? And what we know is that acceleration is the rate of change or the derivative of velocity, all right? So I need to know where velocity is positive and acceleration is positive, or velocity is negative and acceleration is negative. Okay, this graph just shows me velocity, you know, in what's graphed, but I can see where I have a positive acceleration and a negative acceleration, or a positive rate of change and a negative rate of change. Okay, so for instance, we see here that in this first little trapezoidal piece, velocity is positive. Okay, velocity is positive here as well. But now the question is, where is my acceleration positive? And so acceleration is positive on this piece, right? It's also positive here. Why? Because we have a positive rate of change for our velocity, right? So we can say that that's good, right? That's where it's speeding up. We have a problem when velocity is positive and the acceleration is negative or decreasing. Well, the rate of change of velocity is decreasing. And so we've got that happening here. Okay, and then when velocity is negative, which it is below the x-axis, but my rate of change is positive, so that's right here. Okay, we're going to be slowing down. So we could say we're slowing down from 2 to 3 and from 6 to 7. Okay, the particle would be slowing down from 2 to 3 and from 6 to 7. Okay, our reasoning for that is that the particle will slow down when v of t and a of t have different signs, okay, or where the graph is decreasing and above the x-axis, right? That's what we saw right here, okay? It was decreasing but above the x-axis, so that meant we had positive velocity but negative acceleration, or where the graph is below the x-axis but increasing. Okay, and I said 7 to 8, but that should actually be 6 to 7. Okay. All right, we can answer C quickly. When is the particle stopped in changing directions? So looking at the graph, we know it's going to be stopped when we have velocity of 0. That happens right here and right here. Okay. Additionally, we can say that it's changing directions because velocity goes from positive to negative, or vice versa, from negative to positive. Okay, so we have changes of directions, and it stops at 3 and 7. Okay. And then finally for D, on what time interval is the acceleration 0? And so we have acceleration of 0 when, you know, we've got these horizontal line segments. Okay? And so that happens from 1 to 2 and also from 4 to 6. Okay, so we're going to look at a table problem. We're still going to be looking at velocity and time and so forth. And they're asking us at first in this table, where they've given us the time in minutes, and the velocity they tell us is in miles per hour. Okay. They're asking us to find the distance, and they want us to use the trapezoid rule. So remember that the area of the trapezoid is 1/2 times the height times base 1 plus base 2. Okay, this is a little confusing because really this height is the width of the interval, and these two B1 values, they are, really more like heights. They're the function values. They're f of x1 and f of x2. Okay, they're the function values. So if we have a trapezoid, I'm going to draw it like this. I'm not doing a good job. Okay, this would be the height. These two things would be our bases. Okay, so that's what it looks like. So we get these two pieces from the function values. All right. Now, when we multiply these things together, they told us that they want us to do it for, well, we're trying to find the distance probably in miles, right? So when I multiply this, my width, if I'm taking it from these times, is in minutes. I can easily convert that to hours just by dividing the minutes by 60, right? So if I've got 5 minutes, that's 5/60ths of an hour. Okay, so that's why you'll see me take each of these differences for my times and divide it by 60. Okay, so for example, if we want to do it for 0 to 5, then we're going to have an area that's 1/2. My height, or really the width, is going to be 5/60. Okay, and this would be, the units would be hour, right? And then we're going to multiply that by velocity, the sum of the velocities. So 0 plus 18. Okay, the units on this are miles per hour. Okay, and so that means the hours are going to cancel out. What we'll be left with is just miles. Okay, so when we do all of that together, 18 times 5, and we're going to divide that by 120, and we get 3/4, or 0.75 miles. Okay, notice also that this is pretty much the same thing as distance equals rate times the time. Okay, here is my time, and all of this is, including this piece, is kind of my rate. What we're doing when we use the trapezoid rule is averaging those two endpoints. So the 0 plus 18 divided by 2 gives me the average function value for the trapezoid at that point. Okay? Hopefully that was a lot of useful information. Let's look at maybe one or two more. If I wanted to find the distance, okay, remember, we're getting distance because basically we are integrating, right? We're integrating velocity. If I integrate velocity, that gives me distance. When I integrate, that's the same thing as finding the area beneath the curve, right? So by finding the area for the velocity function, we are actually finding the distance, okay? So let's look at one more. Let's look from 25 to 30, all right? We get an area of 1/2, okay, from 25 to 30. Again, we get 5/60ths of an hour. Okay. We're going from 25 to 30, so my function values are going to be 4 plus 36, okay? And again, this is miles per hour, all right? So when I do that, of course, this is going to be 40. So I'm going to cancel that out. We got 20 here. This gives me 100/60 miles, or we're going to have what? 100 divided by 60, if you do that on your calculator, it's going to be 1.66 approximately. Okay, so that's how we find that distance. All right, so I'll go ahead and fill in the rest of the values. You can try out a couple more on your own, but you should get, of course, at the beginning, we've not traveled anywhere. By the time we get to 5 minutes, it's 0.75 miles, and here are the remaining values. Notice that these distances are just the distance traveled over that interval. Okay, part B asks us to come up with the total distance, and so we're going to just add all of these values up. And if we add them all up, we should come up with a total distance of 17.2486 miles. Okay, it says some motion problems will require you to find the actual position of an object or particle at a given time. Remember that you will need to use initial conditions in order to find an actual position, since the definite integral only provides the change in position of an object. That is, when we do, that definite integration, that's the displacement, right? So if I want to know what the actual position is, I need to know where we started. Those are going to be my initial conditions. I'll add to that the displacement, and that gives me my current or actual position. All right, an object moves in a straight line with velocity v of t equals square root of 3t minus 2 meters per second, where time t is in seconds. At t equals 5, the object's distance from the starting point was 12 meters in the positive direction. Okay, so this piece about our initial conditions, very important. Okay, they want us to write an integral that will compute the object's position at 10 seconds. T equals 10 seconds. Okay, so again, we saw this earlier, but if I want to know the current position, I need to know my initial position plus displacement. Okay, and so my initial position is 12. Right? My displacement from the beginning of time over the 10 seconds would be the integral from 0 to 10 of my velocity function. So that's the square root of 3t minus 2 dt. Okay, that's our integral expression for the actual position. Okay, then it says use a graphing utility to find the actual position of the object at 10 seconds. All right, so let's see if we can use our calculator to help us with this. All right, on my y equals list, I'm going to go ahead and put that function in. So I've got the square root of 3x minus 2. Okay, so that's on my y1 list. So in order to actually integrate this, I'm going to get out of here first. And let's see if it'll do all of this at once. We're going to do 12 plus, I'm going to go to math, I can use my up arrow to get to the bottom of the list a little bit faster. Or you could have just pressed 9 if you remember that integration is option 9. All right. And so we're going from 0. Uh-oh. I think I needed to use the arrow. So we're going from 0 to 10. Okay, and I can tell it which function. If I do alpha and the trace key, I can select y1 very quickly, and then dx. Okay. Oh, it didn't like that. I've got the square root of 3. I'm sorry, we don't want to go from 0. We only need to go, I need to go back and make a correction. We only need to go from 5 because they gave us the position of the object at time 5. So let's see if that'll change it. If I change my integration to 5. And if that's not the problem, then I'll take that 12 off. Okay, there it is. Okay, so it didn't like that 0. So 2 things. I want to go back and change what I wrote here. Okay, we're not going from 0 to 10, but 5 to 10. Because they gave us the position at t equals 5. And now that we've done this on the calculator, we can say that it is approximately equal to 34.5088 meters. All right, very good. All right, in question 4, it says a particle is moving along the x-axis with velocity v of t equals negative t squared plus 7t minus 10, measured in meters per second after t seconds, okay, with an initial velocity of s of 0 equals negative 3. Okay, this time we are starting at time 0. Okay, it says determine the displacement of the particle on the interval from 1 to 7. Okay, so if we're looking just from 1 to 7, I'm going to look at the integral from 1 to 7 of negative t squared plus 7t minus 10 dt. Okay, and that's easy enough for us to integrate. We get negative t cubed over 3 plus 7t squared over 2 minus 10t, and we're going to evaluate this from 1 to 7, okay? And so I'll leave it to you to put it into your calculator. I'll write it out. Of course, we're going to have minus 7 cubed over 3, plus, when we put this 7 in, it's also 7 cubed over 2 minus 70. That's what I get when I plug in 7, minus negative 1 over 3 plus 7 over 2 minus 10. Okay, when you do that in your calculator, you should come up with negative 6 feet. So if this thing is moving, it does say along the x-axis, then it's moved in the negative direction or to the left. We might think of it that way, since we got this negative displacement. Okay, now in part B, they ask us what is the total distance traveled by the particle on the time interval from 1 to 7. All right, so, when we think about the total distance traveled, we need to kind of see what's going on with the equation. We need to know, how it's behaving Is it falling below the x-axis or above the x-axis? And we don't necessarily have to see it. We just need to know where we need to break this thing up, okay? So all that said, what I'm going to do is try to find my zeros of this function. I get minus t squared plus 7t minus 10. Okay, I'm looking for the zeros or the x-intercepts. So I'm going to factor out this negative. And now I can factor this as t minus 5 times t minus 2. And so I get x-intercepts, or places basically where this thing could go from positive to negative or negative to positive at t equals 2 and t equals 5. Okay? So I'm going to break my integration up at those points. So we're going to look at the integral from 1 to 2 of the absolute value of v of t dt plus the integral from 2 to 5 of the absolute value of v of t dt plus the integral from 5 to 7 of the absolute value of v of t dt. Okay. And so we've already integrated. We know what the function is. All right, so there's a lot of calculation that has to go on here. I'm going to do a portion of it by hand so that you understand what we have going on here. And then I'm going to use my calculator to do the rest, okay? So if I'm integrating from 1 to 2 for the absolute value of v of t dt, we've already found what this integral was, right? We found what the integral was in this step. Right here. So now what I need to do is plug in the values 1 and 2. Just like earlier we plugged in the values 1 and 7, right? That's going to give me just this portion, right? And then I'll determine if, I need to change it to plus or minus or whatever, right? If it's minus, we're going to make it positive, right? So we get, for this one, plugging in 1 and 2, I'm going to get negative 8/3 when I plug in 2, plus 14, minus 20, okay? And then we got to, I'm sorry, let me go back. I skipped a few steps. Okay, minus 8/3 plus 7/2 times 4. And again, I'm plugging into this thing. So you see we got 7/2. If I plug in 2 and square it, that's going to be times 4 minus 10 times 2. Okay, that's what I get when I plug in 2. I have to subtract from that what I get when I plug in 1. So that's going to be minus 1/3 plus 7/2 minus 10. Okay, from there, I would take that to the calculator. And when you do, you're going to get, in fact, I've already put it in I didn't use the on-screen calculator, but what you're going to get is negative 11/6. But we've got to take the absolute value of that. Okay, all right, so all of that is just, this piece of it, okay? I wouldn't want to have to keep doing that by hand, so let's see what we might get if we use our calculator to do it. So on the calculator, I'm going to go ahead and put in our velocity function for this problem. So we got y equals, I'll use y2 this time. All right. So we got negative t squared plus 7x minus 10. Okay, we've got that there. So now I'm going to integrate. So we're going to go to math, option 9. Okay, I'm going from 1 to 2. Okay, my function is y2. So if I do, trying to get over there, okay, here I am. If I get to alpha and my trace key, then I can get to y2 very quickly. All right, so I'm going to hit enter for that, and then dx. Enter. Okay, so there's that number. But remember, we need to take the absolute value of that number. Okay, so you might record it, maybe you would store it as a particular value. You might write it down, but we got to have the absolute value of that. To make this a fraction, of course, we can do math, and the first option there is fraction. And so it writes it as a fraction as negative 11 over 6. So for that first piece, we're going to have 11 over 6. Now I need to repeat this, and of course, to repeat it very quickly, I can just do second enter. So second enter. Okay, I'm going to go second enter again to take me back one more step. And now the only thing I really need to do is change my limits of integration, right? So I'll just come over here. And this time we want to go from 2 to 5. And so we get 4.5. That's already positive. So we got 11 over 6 plus 4.5. And then for the last piece, we're going to go from 5 to 7. So just second, enter. And we're going to have 7 as our upper limit and 5 as the lower. And I can convert that to a fraction, math, fraction. All right, so we're going to use 26 thirds. Because we're doing distance, we want this to be positive, right? So 26 thirds. So I got 11/6 plus 4.5 plus 26 thirds. All right, and that gives us 15. Okay, so looking back at the problem so that we can put this in context. Okay, we were trying to find the total distance traveled on the interval from 1 to 7. And when we added all of these pieces together, for this one we got, when we did the absolute value, we got 11 over 6. And for this one, we got 4.5. And for this one, we got 26 thirds. Okay, but we let the calculator do some of that work for us. When we added it all together, we get 15. And our units in this case would be feet. All right, let's look at another problem. Example 5. Suppose you're driving in traffic behind a large bus at 66 feet per second. This is 45 miles per hour. Sounds a lot faster, but anyway, 66 feet per second. When you finally get a chance to pass, you step on the accelerator, giving the car an acceleration of a of t equals 4 over the square root of t, where a is measured in feet per second, and is measured, I believe time is measured in seconds. How fast are you going 16 seconds later when you have passed the bus? Okay, all right, so we've got a lot going on here, but still, this is kind of like trying to figure out position, current position, except now we're doing acceleration, but when we back this thing up, what it's going to give us is the current velocity. Okay, so here's what we know in summary. Okay, we've got our function for acceleration. Okay, we're going to use this to figure out what our velocity is. V of t is going to be the integral of a of t, so 4 over the square root of t dt. Okay, that's how we're going to find our velocity. All right, if we go on and do that, then of course this is the integral of 4 times t to the negative 1/2 dt. Okay, what I would do here is add 1/2. So we got 4. This is going to be t to the 1/2. We would divide by 1/2, but that's the same thing as multiplying by 2, right? So plus c. We've not put any limits on here yet, so don't forget about our constant. So what we have is 8 t to the 1/2 plus c. Okay, now that we've got that as our velocity, we have some information. We know that the initial velocity was 66 feet per second, right? Or 45 miles per hour. I think we're going to do this in feet per second. So if v of 0 is 66 feet per second, that's my initial point. I need to add that here. Or another way of thinking of it is this, is if I take this information and plug it in here, we can solve for c, right? We can say v of 0 is going to be 8 times 0 to the 1/2 plus c, right? I'm just plugging in to what we just found, and this should be equal to 66, right? When I do that, of course, this is 0, and so we get c is equal to 66. So my function is going to be 8t to the 1/2 plus 66. Okay. Now, if I want to know how fast I'm going when I've passed this thing 16 seconds later, then we're going to plug in 16. Okay, so we can say v of 16 is equal to 8 times the square root of 16, right? T to the 1/2 is the square root plus 66, or 8 times 4 plus 66. And so we get 98 feet per second. All right, so still, note here that we basically kind of use that same principle of new position. Okay, I mentioned it earlier and I'll mention it again here, right? If I wanted to get the new position, then I would start with whatever my initial condition was, which in this case was 66 miles per hour. And then to get the displacement, we would basically integrate from 0 to 16. V of t dt. Okay, so that's another way we could have approached this problem, and we would get the same answer. So if I wanted to use my calculator to help me with this, I would put the function on my y equals list. So this is the acceleration function. We got 4 divided by the square root of x, okay? And again, our initial condition is 66. And then I'm going to integrate. So we go to math. Number 9 is integration. We're going from 0 to 16. Okay, and you might ask, well, why am I not, trying to figure out where there's zeros? Well, we know that if we're talking about 1 over the square root of x, it's only going to be equal to 0 when x is 0. It's not coming back across the x-axis between 0 and 16. So I kind of mentally checked for that. Okay. And then we're going to go to alpha, trace. This is my third function, y3, and dx. Okay, we'll hit enter. And it gives us 97.999. The calculator is probably having some round-off error since we did this by hand and we were able to get an exact value. So, with those values, either if you use the calculator and you get something this, definitely do approximately. But, if you did it by hand, then we can see that it was exactly 98 feet per second. Okay. By the way, real quickly, I did want to just back up a second to example 4, where we broke it up at 2 and 5, and I just wanted you to see what that looks like. So I'm going to say y equals negative x squared plus 7x minus 10. Okay, and so when we look at this graph, we can see that, before 2, we had negative values. Between 2 and 5, there were positive values. And then after 5, we were negative again. So we needed to break it up at these zeros to make sure that we applied absolute value to the places where the function was negative. Okay, also, since we're looking at it, let's just take a quick look at y equals 4 divided by the square root of x. That's the one that we just did. Okay, and so again, you can see here that there's no reason for us to be concerned about this actually crossing the x-axis, because the only place that it would have crossed the x-axis, or we would have had a concern about that, is when x was equal to 0. And so we were looking from 0 to 16, and so everything is okay there. Okay, let's recap. So in this problem, we were given acceleration. We were also given our initial velocity, and we were able to use integration to help us come up with the velocity equation, the integration plus that initial condition. All right, so this is where we are Now, once we got velocity, or the equation for velocity, we were able to find our velocity at a particular time. Okay? So when we integrate acceleration, we get velocity. The next question asks us about how far we traveled during that time. So now they want us to find distance. And in order for us to find distance, we're going to have to integrate velocity. All right, so our distance formula, or S of t, is going to be the integral of our velocity equation. So 8t to the 1/2 plus 66 dt. Okay. And again, since we're talking about distance, technically this should be the absolute value of our velocity function, right? So I'll just go ahead and put the absolute value around it that way. Okay, we're going to be looking at this from 0 to 16. Okay, they didn't tell us anything, I don't think, about an initial position. So we'll just assume, and of course they're asking us how far we traveled. So essentially, that's just the travel, not where we ended up, but how far we traveled. Okay, so let's integrate this. We could use our calculator if we wanted to, but we would get it's going to be 8t to the 3/2 divided by 3/2, so that's the same thing as times 2/3 plus 66t. Okay, and we're going to evaluate this from 0 to 16. Okay, I can see that when I plug in 0, I'm just going to get 0. So really, I just need to look at what happens when we plug in 16. And I can also, let's see, well, that's going to be 16/3. Okay, so when we plug in 16, we got 16. We can think of this as the square root of 16 to the 3rd power, right? So that's going to be 4 to the 3rd power, which is 64. So 16 times 64, at that point I'd get my calculator, over 3. So I got 1,024 over 3 plus 66 times 16. And we get 1,056. All right, when we add these two together, it's approximately 1,397.33, and this is going to be in feet. Okay. Again, notice that neither of these values came up to be negative. But if they had, we would take the absolute value of them to make sure that we got distance, okay? Finally, in C, they ask us, what is our average velocity for the 16-second interval? And, we don't want to overthink this problem, okay? We know how far we traveled during the interval, right? And we know how much time. So that's average velocity. When you go on a trip, you look at how far you have to go, you look at the time it takes you to get there. That's going to give you your average velocity, okay? When we divide, right? That doesn't mean that's the time that you were going or the rate that you were going at any particular moment. It's just the average velocities, So it's displacement over time. Okay, and let's not use displacement. Let's just use distance, right? Because we looked at the whole thing. Okay, and so we'll take the number that we just calculated, 1397.33. We're going to divide that by 16. And so we get an average velocity for the interval of approximately 87.33 feet per second. Okay, that was a long problem. All right, let's see if we can kind of repeat it. Here we're going to drop our calculus book. We'll do this the day after we take the AP exam. It says we drop it from a window that's 48 feet above the ground. How long will it take your book to reach the ground? Okay, so if you think back to algebra, you've seen this type of problem before. When we talk about how long, so that means time, will it take your book to reach the ground? If the book is on the ground, that's a position, right? And so on the ground would be a height of 0. So we want to know, when will the height of the book be 0? Okay, so kind of think on that. Now let's look at what they've given us so far. Okay, as far as velocity, they didn't say that it was flying when it went out the window. So we're going to assume that our initial velocity is 0. Okay. As far as acceleration, we'll just use the constant used for that. Okay. When things are falling, we use, in a simple model, we just use negative 32 feet per second squared. Okay, so we're going to use that since they didn't tell us anything else about the acceleration of the object. Okay, and the other thing that we know is that at the beginning of this process, the position of the object was 48 feet. Okay, so that's what we know. That's where we're starting. All right, and so what I'm going to have to do again is use my acceleration function to get velocity, and then we're going to use velocity to get position. Okay, so we'll start by saying velocity is going to equal the integral of negative 32 dt Okay, so we get negative 32t plus c. That's going to be our velocity function. Okay, but again, we believe that the initial velocity was just 0, so we'll just leave it at negative 32t. Okay. All right, so now I'm going to try to find my position function. And so we get s of t equals the integral of negative 32t dt. When I integrate that, we're going to get negative 32t squared over 2 plus c. Okay. We don't just ignore the c, but if we, use our initial conditions and it comes up to be 0, then 0 is what it is. Okay, so, but for this one, we've got an initial condition of 48 for our height. So I know that s of 0 which is negative 32 t squared over 2. I can call that 16. Okay, plus c, it should be equal to 48. All right, so when I go on and solve for that, okay, and we could just put the 48 in. If that's our initial condition, and then we integrate it, then we really don't have to go through the step of solving, right? That's kind of the point of what we're looking at here. So I'm just going to go ahead. If you want to, you can integrate it to get to see that c really is 48. Actually solve for it, I mean. Plug in 0 for t, and then solve for c, you'll get 48. All right, but what we know is s of t is negative 16 t squared plus 48. Okay, and what I want to know is when this thing is equal to 0. And so if we can solve that, we'll have the answer to the time at which your calculus book will have hit the ground. So we got minus 16 t squared equals negative 48, or t squared equals 3. So t is going to be plus or minus the square root of 3. Of course, we know we can't have negative time, so the time at which the book hits the ground would be square root of 3 seconds. Okay. All right, so then now that we know when it hits the ground, the last question is, what is the velocity of the book at the instant it reaches the ground? And so we have an equation in our work for velocity. Velocity is negative 32t. So we want to find the velocity at time square root 3. So negative 32 times the square root of 3. Okay, when we get that, if we do that out on your calculator, you'll get approximately negative 55.426 feet per second at impact. All right, final question has 4 parts, but we can make it. The particle moves along the x-axis so that its velocity at time t for 0 less than or equal to t less than or equal to 15 is given by a differentiable function v whose graph is shown below. Okay, so we've got the graph of velocity. At time t equals 0, the particle is at x equals 4. Okay, so this tells us something about the position of the particle, not the velocity. The velocity is 0 at t equals 3 and t equals 9. Okay, we can see that on the graph. All right, and t equals 13. Velocity is 0. The graph has horizontal tangents at t equals 6 and t equals 9. The areas of the region bounded by the t-axis and the graph of v on the intervals from 0 to 3, so that's here, 3 to 9, 9 to 13, and 13 to 15 are 6, 9, 3, and 2 respectively. They've given us a lot of information. Okay, so let's see what they're going to ask us about that. Okay, it says for 0 less than or equal to t less than or equal to 15, find the time and position of the particle when the particle is farthest to the right. Justify your answers. All right, so if we look back at the graph, you know, we could reason that it's either going to be farthest to the right at time equals 3, t equals 3, or t equals 13. Because after that, it starts moving back to the left because we are below the x-axis. right? So we know it's not happening at t equals 9, right? Because at t equals 9, we just stopped from moving back to the left, right? So it's either going to have to be at t equals 3 or t equals 13. Okay, the question asks us about the position. So what we're going to do is to use our initial condition, which they gave us, right? At time t equals 0, the particle is at x equals 4. So I can figure out where this thing is at t equals 3. Okay, at t equals 3, it's going to be 4 plus the integral from 0 to 3 of v of t dt. Okay? And we know that the integral from 0 to 3 of v of t dt is just 6. So we get 4 plus 6 equals 10. Okay, well now, let's see where it is at t equals 13. Okay, and we're just kind of looking at, the displacement. That's what really matters. So I'm not doing absolute value, right? So we're going to do 4 plus the integral from 0 to 13 of v of t dt. Okay, and we could have broken it up if we wanted to, but what's most important is that we understand what to do with this interval. We've got 4 plus 3 minus 9 plus, I'm sorry, it was 4 plus 6 minus 9 plus 3. Okay, 4 plus 6 minus 9 plus 3. All right, and so what we get for that is just 4. Okay, all right, so the answer to the question is, when is the particle farthest to the right? And we're going to say that happens at time equals 3. And the reason we can say that is because the velocity is positive, greater than 0 for those two intervals. Okay, v of t, this is why we chose those two. V of t is greater than 0 for 0 less than or equal to t, well, probably just less than t, less than 3, and 9, I believe it is, less than t less than 13. So these are the places where, velocity was going in that direction, and so this is when we could have been farthest to the right. Okay? All right, in part B, it says how many values of t, or for how many values of t, is the particle at x equals 4. Okay? So, looking again at our graph, we know that our initial position was 4. Okay, so we can think about that. Does that work? All right, and then after that, once we got to 3 seconds, it's going to be at 10. 4 plus 6 gives us 10. Okay? But then, at 9 seconds, it would have come back to a position of 1. And in order to get from 10 to 1, we have to go through 4. So far, twice, right? It happened at 0. So, okay, and then now we're saying at somewhere between 3 and 9, it happened again. So, Okay, that's another place that would have happened. So at this point, x is equal to 1, right? That's what we said. X is equal to 1. And now I'm going forward to a value of 4. So it looks like it happens at x equals 13, or rather t equals 13. All right, but from there, we're just going backwards from 4. And so altogether, it looks like there are 3 values. By the intermediate value theorem, there are 3 values for t where the particle is at 4. Okay, so again, to recap, it started out at 4. Okay, started out at 4. X was equal to 4 at this point, because they told us that, right? At time equals 0, x was equal to 4. Then it moved forward. So once we're going forward all the way to 10, 4 plus 6 is 10, then we don't have to worry about 4 again. But when we start to move backwards right here, then somewhere between 3 and 9, we have to hit 4 again. At t equals 9, the actual position is 1. And so if we add 3 to 1, we hit 4 again right here. And then once we get beyond 13, it's going in the opposite direction. So there were 3 places where it was equal to 4. All right, in part C, the speed of the particle is increasing on the, the question is, on what interval is the speed of the particle increasing? Give a reason for your answer. Okay, so we talked about this a little bit earlier. We've got a graph of velocity, okay, and we can tell about the sign of acceleration. And when the sign of velocity and the sign of acceleration are the same, then we're going to be increasing. So in this case, I'm going to clear this. Okay, in this case, we've got a positive velocity, right here, but our acceleration is negative. So that's not what we're looking for. Okay, we don't want this one. All right, here we've got negative velocity. By here, I'm talking about this piece, negative velocity and negative acceleration. All right, so it looks like we'll come back and talk about what those points are a little bit later. All right, in this next little piece, velocity is negative, but acceleration is positive. So here it would be slowing down, right? Here we've got positive velocity and positive acceleration. All right, and I think you probably got the idea now. In this next little interval, velocity is positive, but acceleration is negative. And in the next interval, velocity is negative and acceleration is negative, okay? So where I've highlighted in green, that's where we would be speeding up. And so that's going to be from 3 to 9. I'm sorry, not 3 to 9, 3 to 6, right? So 3 to 6, okay, then from 9 to 11, and then from 13 to 15, okay? So the speed of the particle is increasing from 3 to 9, and then from, I'm sorry, not 3 to 9, 3 to 6. And then from 9 to 11. And then from 13 to 15. right? And this is because the sign of both velocity and acceleration are the same at that point, or at those, on those intervals. All right, last question. D, during what time intervals, if any, is the acceleration of the particle positive? Justify your answer. So remember that acceleration is the rate of change of velocity. So basically, when our velocity graph has a positive rate of change, then we're going to get positive acceleration. All right, so that happens about here. Okay, that was supposed to be a curve, but you get the idea. Okay, so, and that's about it, right? So it looks like we're going to only have that positive acceleration from 6 to 11. Okay, and remember they gave us really careful information about where we had those horizontal tangent lines at 6 and 11, so I can know that it's exactly happening. It's changing from increasing to decreasing at exactly those points. Okay? All right, if you have any questions about this, we'll talk about it in class.